All right, today we're going to put on our detective hats and crack a classic chemistry case file. Now, it might look like a standard exam question, but trust me, this thing is a first-class mystery just waiting to be solved.
Can a chemistry problem be a mystery? Oh, absolutely. You know, every problem gives you a set of clues, some suspects, and a challenge to solve using the laws of science. And this one? This is a fantastic case. So let's meet our primary suspects.
So, here's the scene. We've got two beakers, and each one has a different silver salt that just won't fully dissolve. You've got that solid stuff sitting at the bottom. And our first mystery is this: which one of these solutions is actually hiding more dissolved silver ions?
Okay, let's kick off our first investigation. It's time to interrogate our suspects, silver chloride and silver carbonate, and find out which one is really letting more silver ions loose into the solution.
Now, the most crucial clue we have is this thing called the KSP value. You can think of it like a unique chemical fingerprint for each compound. It's basically a hard rule that dictates exactly how much can dissolve. And you might look at silver carbonate's KSP, see that it's lower, and think, case closed, it's less soluble. But there's a twist.
And here's where it gets really interesting: the dissociation. See, when silver chloride dissolves, it's a simple one-to-one deal. One silver ion, one chloride ion. But look over at silver carbonate. For every single unit that dissolves, bam, it releases two silver ions. This 2-to-1 ratio, that's a critical piece of evidence.
And you know what? That 2-to-1 ratio, it changes everything. Once you factor that into the calculations, it turns out the beaker with silver carbonate actually has a higher concentration of silver ions. So yeah, its KSP is smaller, but that little 2-for-1 special is what puts it way ahead. Mystery number 1 solved.
All right, on to our second investigation. The scene is totally different now. We're the ones mixing the chemicals, and our job is to predict if a crime, that is, precipitation, is about to happen. And this isn't just some random problem. It's the very same principle that explains how things like kidney stones can form or how minerals get deposited in rock formations over millions of years.
So, how do we solve this? Well, we don't guess. We follow a procedure. Think of this as our detective's protocol. 4 clear, simple steps that will lead us straight to the truth.
First things first, we gather the evidence. Okay, so we've got our source of silver ions, we've got our source of carbonate ions, and we know the total volume of the solution. This right here, this is our crime scene, and these are the actors involved. Now for the key part of the analysis. We're going to calculate something called QSP. Now, if KSP is the law of solubility, then QSP is like a snapshot of what's happening right now. We're basically asking, are the ion concentrations in our beaker breaking the law? Okay, we've taken our snapshot, we've calculated the QSP value based on all our evidence, and we've compared it to the KSP for silver carbonate. All the evidence is in, so what's the verdict? Is a crime being committed?
Yes, absolutely. The QSP value is way bigger than the KSP value. That means the law has been broken. The solution is supersaturated with ions. They literally have no choice but to crash out of the solution and form a solid. Case closed on that one.
Okay, now for our final and maybe most interesting investigation. The mystery shifts. We've seen salts dissolve and precipitate, but what about the ions they leave behind? This time we're focusing on that carbonate ion from our earlier case. We need to figure out its effect on pH, first when it's just by itself, and then when it's challenged by a strong acid.
So we start with what looks like a simple solution of potassium carbonate. But here's the thing, it's not neutral at all. The carbonate ion, it's actually a weak base. It goes around pulling protons from the water molecules around it. And what does that do? It creates hydroxide ions, which makes the whole solution alkaline or basic.
But this is where the case gets really good. We're not just watching anymore, we're getting involved. We're going to add a dose of strong hydrochloric acid right into the mix. So the big question is, how will our basic carbonate solution react to this sudden, massive acidic stress?
So the acid comes in and neutralizes most of the carbonate. But in doing that, it creates something new. It's conjugate acid, bicarbonate. So now look what we have. We have a mixture of both a weak base and its conjugate acid. And that, my fellow detectives, is a buffer solution. It's the exact same kind of system that keeps the pH of your own blood incredibly stable, day in and day out.
And you know, whenever you have a buffer, you get to bring out the master tool for the job, the Henderson-Hasselbalch equation. This thing is amazing.
It lets us take that new ratio of our base and its conjugate acid and calculate the final pH of the solution with pinpoint precision. It is the final crucial calculation in our case.
And there we have it. We've gathered the clues, we've followed the procedures, and we've solved every single part of this multi-stage mystery. So before we file this case away, let's just quickly review the fundamental principles we uncovered during our investigation. So here's the crucial takeaway. These rules aren't just for solving exam questions. KSP, QSP, hydrolysis, buffers, these are fundamental principles that govern everything, from the chemistry of our oceans to the incredibly complex biochemical balancing act that's happening inside our own bodies right this second.
So what we've really done today is shown how you can take a complex case and break it down into a series of logical, totally solvable investigations. These principles, these detective tools, they're yours now. And believe me, the world is just full of chemical mysteries, so go out there and start solving them. Thanks for watching.